Okay, we are done talking about sequences and series of numbers. What we're going to do now is talk about sequences and series of functions, right? So that's kind of the next logical step here. And this is really the reason that we're interested in determining convergence of series in general, is because we want to be able to look at power series, which is the topic of discussion in 9.9. In order to get there, we're going to look at some specific cases of power series called Taylor and Maclaurin series, and that's the topic of discussion in 9.8. And so in order to get to Taylor and Maclaurin series, we have to start with Taylor and Maclaurin polynomials, which is the topic of discussion now in 9.7. So we'll get back into infinite series and questions of convergence and divergence in a couple of sections from now. And when we get there, we'll be talking about convergence of series of functions, series of polynomials. So it's exciting stuff, but let's get into it. So the reason that Maclaurin and Taylor polynomials pop up is because they are approximations for functions. So they're polynomial approximations for functions that potentially might not be very nicely behaved functions, but nevertheless can be approximated under certain conditions with polynomials. And so it's a really nice result. And so here's how the Maclaurin polynomials are defined. So if f can be differentiated n times at x equals 0, then we define the nth Maclaurin polynomial for f to be this piece of work here, right? So it's the sum from k equals 0 to n of the kth derivative at 0 divided by k factorial times x to the k power. So as I said, as long as x is pretty close to 0, this is a really good approximation for the function f. Okay, which is a nice thing if f is something like a natural log, for example, and you want to write a computer program to approximate the value of the natural log of different numbers. Well, being able to write that natural log as a polynomial instead of as a natural log is really useful, right? It's going to come in handy for that. So anyway, so we like these things. Polynomials are much more nicely behaved than a lot of like transcendental functions. So now, how close to 0 you have to be in order for this to be a good approximation is a question that we're going to want to answer, and it's something that we will talk about within the course of the next 3 or 4 lectures. Okay, so how close to 0 we need to be, and how good the approximation really is. Those are both questions that we'll want to explore over the next few sections. This concept of approximating a function with a polynomial is actually not a new thing. You may recall back in Calc 1 that you learned about something called the local linear approximation for a function. Well, as it turns out, P1 of x, so if you just go from 0 to 1, right? So just the first 2 terms of this series, right? P1 of x is the local linear approximation that you learned about in Calculus 1. So anyway, let's practice finding Maclaurin polynomials for some things. So the first example we'll do is for e to the x, and in the second example we'll do this for sine x and cosine x. So these are some of the most common ones. So let's see if we can find the Maclaurin polynomials for those things. Okay. Okay. So we want the Maclaurin polynomials for e to the x. Okay. All right. Well, as you can see, the Maclaurin polynomials require us to look at a bunch of derivatives, right? This is the kth derivative of f evaluated at 0. So let's find some derivatives of e to the f, or e to the x. Well, that's not very interesting, right? So first of all, f of x is e to the x. That means that f prime of x is e to the x, and f double prime is e to the x, and so forth, right? So that's really boring. The nth derivative of e to the x is still just going to be e to the x, right? When we evaluate these things at 0, we're going to get 1, right? E to the 0 is 1. So the nth derivative of e to the x evaluated at 0 is going to be 1 as well. So with that in mind, we can write down the first several Maclaurin polynomials, right? So p sub 0 is going to be f of 0 divided by 0 factorial times x to the 0 power. 0 factorial is just 1. F of 0 is also 1. And x to the 0 is 1. So this is just 1. Right? So there's p0. p1 is going to be f prime of 0 divided by 1 factorial times x to the first power. Or actually, I should start at 0, right? I should start at just f of 0 divided by 0 factorial times x to the 0, and then add f prime of 0 divided by 1 factorial times x to the first power. That would be the first one, right? Because you have to start at 0 and then end at n, and in this case n is 1. So there's p1. Anyway, f of 0 is 1, 0 factorial is 1, x to the 0 is 1. 1 divided by 1 times 1 is 1. Okay? F prime of 0 is also 1, 1 factorial is also 1, x to the first power is x. So there's p1. p2. And really I should say, these are functions, so I should be calling this p0 of x, p1 of x. p2 of x is going to be f double prime of 0 divided by 2 factorial times x squared plus f prime of 0 divided by 1 factorial times x to the first power plus f of 0 divided by, see, I keep wanting to do this backwards, but anyway, it still works. F of 0 divided by 0 factorial times x to the 0. Really, I should start here and do this one, then this one, then this one. I don't know why I keep working backwards, but anyway, I'm going to put them back in order, right? So this one was 1, this one was x, and then this one is 1 over 2 factorial. 2 factorial is 2, so this is 1/2 x squared. I'm just going to call that x squared over 2. Let's do one more. I'll try to do this one in order. So I need to start at 0. So it's going to be f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. Right? So that's p3. And that's going to come out to 1 plus x squared over 2 plus 3 factorial is 6. So this is going to be 1/6 x cubed. So x cubed over 6. And so forth, right? If we keep going, the nth Maclaurin polynomial is going to be 1 plus x squared over 2 and so forth until we get to, well, notice that this is x to the 0 over 0 factorial, x to the first over 1 factorial, x squared over 2 factorial. So it's going to go up to x to the n over n factorial, right? So there's the nth Maclaurin polynomial for e to the x. So my claim is that this thing approximates e to the x really well. And I think maybe not in this lecture, but maybe in the next one, I'll show you some of these things in Desmos. They're really cool to kind of look at. You're welcome to look at it yourself, right? You could put, you could go up to like I don't know, x to the 7th over 7 factorial or something, and then plot that together with e to the x, and you'll see that at least when you're really close to 0, you get a very nice approximation. So, so that's that one. Let's see if we can do the same thing for sine and cosine. These ones are a little trickier, but let's see if we can do them. Okay, so if f of x is sine of x, then f prime of x is cosine x, f double prime of x is negative sine x, f triple prime is negative cosine x, and the fourth derivative would be back to positive sine. And then it's going to repeat, right, over and over and over again. Well, so let's see what these are when we evaluate them at 0, right? So f of 0 is sine 0, that's just 0. F prime of 0 is cosine 0, that's 1. F double prime of 0 is negative sine of 0, so that's 0 again. F triple prime of 0 is going to be negative cosine of 0, so that's negative 1. And then at the fourth derivative, evaluated at 0, we're going to be back to 0. Okay, so that's interesting. It alternates, right? 0, 1, 0, negative 1. 0, 1, 0, negative 1. 0, 1, 0, negative 1, and so forth. So, if we write out the first few Maclaurin polynomials, we could say P0 of x is f of 0 divided by 0 factorial times x to the 0. In this case, f of 0 is 0, so this whole thing is 0. P1 is going to be f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first. That's going to be 0 plus f prime of 0 was 1, so 1 over 1 is 1. This is just 0 plus x, so it's just x. P2 is f of 0 over 0 factorial x to the 0 plus f prime of 0 over 1 factorial x to the first plus f double prime of 0 over 2 factorial times x squared. That's going to be 0 plus x plus f double prime of 0 was 0 again. Let's do a couple more. P3 is going to be f of 0 over 0 factorial x to the 0 plus f prime of 0 over 1 factorial x to the first plus f double prime 0 over 2 factorial x squared plus f triple prime 0 over 3 factorial x cubed. That's going to be 0 plus x plus 0 minus, right, because f triple prime is a negative one, is going to be minus x cubed over 3 factorial. So that would be x cubed over 6. Okay. If we go one more, the next term is just going to be 0, isn't it? So I'm not even going to write down all the nitty-gritty. I'm just going to say that I know that P4 is going to be 0 plus x plus 0 minus x cubed over 6 plus 0. Okay, so that's kind of interesting. So one thing to note is that each even term, right, each even order Maclaurin polynomial is just the odd order Maclaurin polynomial that came before it, right? So P2 is the same as P1, and P4 is the same as P3. because every other term is a 0. Okay? So writing down a general rule for this is maybe a little bit tricky, but we could maybe say it something like this. We could say, well, if every even Maclaurin polynomial is the same as the odd numbered Maclaurin polynomial that came before it, then we can say something like p sub 2k plus 2 is equal to p sub 2k plus 1, right? They're really the same thing. And what is p sub 2k plus 1 going to be? Well, it's going to be 0 plus x to the first over 1 factorial plus 0 plus x to the third over 3 factorial plus 0 plus x to the fifth over, the signs alternate, right? So it's going to be something like this. It's going to be something like x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial, and so forth until we get to 2k plus 1. So it's going to be, the only thing that's bothering me is this negative. So what do we do about the negative? Well, that's also going to be, okay, so it's going to be negative 1 to the 2k plus 1, x to the 2k plus 1 over 2k plus 1 factorial. Ooh, I better double check that before I put my stamp of approval on it. Let me pull out the book and make sure that I got that right. X to the 2k plus 1 over 2k plus, yep. Oh, but negative 1 to the k. It's just negative 1 to the, negative 1 to the k, right? Oh yeah, it would have to be. Otherwise, this would be positive every single time. So yeah, just negative 1 to the k. Just negative 1 to the k. Yeah, okay. That way, the sign will actually alternate. Okay. Yeah, so for example, if k is 4, then this would be, then p sub 4 times 2 is 8 plus 2 is 10. So p sub 10 would be the same thing as p sub 9. And we would go, again, k was 4. Negative 1 to the 4th is positive 1. And sure enough, right, the next term, the x to the 9th over 9 factorial should be positive. Yeah, okay, so this checks out. This checks out. Okay, so I'm happy. So this is good. So there you go, right? That's the Taylor polynomial for sine. Okay, let's do another one. Let's do the Taylor polynomial for cosine. Let's do this one, and then we'll talk a little bit. Okay, so same thing, right? We've got to take a bunch of derivatives. F prime of x here is going to be negative sine x. F double prime is going to be negative cosine x. F triple prime is going to be sine x. And then f, the fourth derivative, we're going to be back to cosine where we started. So if we evaluate these things at 0, this time we're going to start at 1, and then go to 0, and then go to negative 1. So it's the same pattern, but it's just starting at a different place. One, 0, negative 1, 0, 1, 0, negative 1, 0, etc. Okay? So the 0th order Maclaurin polynomial is going to be f of 0 over 0 factorial x to the 0. And that's going to be f of 0 is 1, 0 factorial is 1, x to the 0 is 1. So that's just 1. the first order Maclaurin polynomial is going to be f of 0 over 0 factorial x to the 0 plus f prime of 0 over 1 factorial times x to the first. That's going to be 1 plus, well, f prime of 0 is 0, so this one's going to be 0. The second order Maclaurin polynomial for cosine x is going to be f of 0 over 0 factorial x to the 0 plus f prime of 0 over 1 factorial x to the first plus f double prime of 0 over 2 factorial x squared. So that's going to be 1 plus 0 plus, or minus actually, minus, because f double prime of 0 is negative, so it's going to be minus x squared over 2. Let's do a couple more, and then we'll try to write down a general rule. So the third order is going to be f of 0 over 0 factorial x to the 0 plus f prime of 0 over 1 factorial x to the first plus f double prime of 0 over 2 factorial x squared plus f triple prime 0 over 3 factorial x cubed. That's going to be 1 plus 0 minus x squared over 2 plus 0. Kind of anticlimactic, but one more. I already know this is going to be 1 plus 0 minus x squared over 2 plus 0. And then I'm going to have a plus f fourth derivative evaluated at 0 divided by 4 factorial times x to the fourth. And that's going to be 1 plus 0 minus x squared over 2 plus 0. And then f to the fourth is 1, or fourth derivative rather, is 1. 4 factorial is 4 times 3 is 12 times 2 is 24. So it's going to be plus 1 over 24 x to the fourth. So maybe I'll just call it x to the fourth over 24. Okay, give me a second, see what my dog's barking at. Okay, so notice the same thing happens this time. Well, sort of the same thing, not quite. Each odd numbered term, or each odd numbered order is the same as the even numbered order that came before it, right? So if we wanted to write down like a general formula, let's say P, well, if it's an odd term, we could call it maybe 2k plus 1. That's going to be the same thing as P sub 2k, right? They're the same thing. And what's it going to be? Well, it's going to be 1 minus x squared over 2 plus, maybe I'll write that as a factorial, just make it easier on myself, plus x to the fourth over 4 factorial. So then I suppose it's going to be minus an x to the 6 over 6 factorial, and then plus an x to the 8th over 8 factorial, and so forth, until we get to, so we're going to have a negative 1 to the something in order to get it to alternate. And then we're going to have an x to the 2k, it looks like, divided by a 2k factorial. So what should this be, k or k plus 1? So if k is, let's say, 2, then P4 should end here at x to the fourth over 4 factorial. And we need it to be positive. So I think this is just going to be k then. Right? That way when k is 4, we get a positive. When k is 2, or no, yeah, when k is 2, we end at 4, and we get a positive. When k is 1, we end at 2 times 1 is 2, so we end here, and we should get a negative. Yep, okay, so this will do the trick. So there you go. Okay, so there's the Maclaurin polynomial for cosine x. Okay, So the title of this section is Maclaurin and Taylor Polynomials. We've talked about Maclaurin polynomials. We haven't talked about Taylor polynomials yet. They're the same thing, really. So it's really not a whole lot of new information. Okay. So if f can be differentiated n times at x naught, then we define the nth Taylor polynomial for f about x equals x naught to be this monstrosity. So I can't put them both on the page at the same time without zooming out to the point where you can't read anything. Okay, but if you compare this to what we wrote down for the nth Maclaurin polynomial, you'll notice that with the Maclaurin polynomial, x naught is 0. So this is a 0, and this is just x to the k, because x minus 0 is just x, right? So the nth Maclaurin polynomial is really just the same thing as the nth Taylor polynomial about x equals 0. So the Taylor polynomials are sort of a generalization of the Mclaren polynomials. The Mclaren polynomials are always centered at 0. The Taylor polynomials could be centered at any number x naught. Okay? So let's find the first 4 Taylor polynomials for the natural log of x about x equals 2. And they're not asking us to come up with a general formula. They just want the first 4. That's nice for us. Okay, let's do it. So in my notes it said example 3, but I'm pretty sure I'm on example 4. So f of x equals ln of x, and we want this about x equals 2. All right, so let's do this. So, f of x is ln of x. F prime of x is 1 over x. F double prime of x is going to be, well, this is x to the negative 1, so it's negative x to the negative 2, right? So negative 1 over x squared. F triple prime. This is negative x to the negative 2, so it's going to be positive 2 over x cubed. How many did they want? They wanted the first 4 Taylor polynomials. Well, I don't know if that includes the 0th one or not, so I'm just going to go one more just for good measure. That's going to be a negative 6 over x to the 4th. Okay, and now let's evaluate this thing. This time we're not going to evaluate at 0, we're going to evaluate at 2. Okay? Hmm. 2 cubed is 8. 2 over 8 is 1/4. And 2 to the 4th is 16. 6 over 16 will reduce to, oh, come on, I can't do math in my head anymore. 3/8. Yeah, it reduces by 2. Okay, so negative 3/8. Give me a second. 2x to the negative 3. 2 times negative 3 is negative 6. Yeah, so it's negative 6 over x. Okay, all right. Okay, so the 0th Mclaren, not Mclaren, Taylor. We're working with Taylor now, right? So the 0th Taylor polynomial is going to be f of 2 over 0 factorial times x minus 2 to the 0. Okay. So that's ln of 2, that's 1. And this is just 1. Anything to the 0 power is 1, right? So this is ln of 2. It's just ln of 2. Okay, the first Taylor polynomial. is going to be f of 2 over 0 factorial times x minus 2 to the 0 plus f prime of 2 over 1 factorial times x minus 2 to the first. That's going to be ln of 2 plus, this is 1/2, this is 1, so it's going to be 1/2 times x minus 2. Okay. The second Taylor polynomial is going to be f of 2 over 0 factorial times x minus 2 to the 0 plus f prime of 2 over 1 factorial times x minus 2 to the first plus f double prime of 2 over 2 factorial times x minus 2 squared. That's going to come out to ln 2 plus 1/2 times x minus 2 f double prime of 2 is negative 1/4, and negative 1/4 times 1 over 2 factorial. So 4 times 2 factorial is 8, right? So that's negative, so it's going to be minus 1/8 times x minus 2 squared. Now we could simplify that for sure. I mean, we could FOIL this out and combine like terms and then distribute the 1/2 here, combine like terms and everything. Oh, goodness gracious. Should we do that? Let me see if the textbook wants you to do that. No, the textbook is okay with you leaving it this way, and so am I, frankly. I mean, who wants to go through all that? Okay, P3 is f of 2 over 0 factorial times x minus 2 to the 0 plus f prime of 2 over 1 factorial times x minus 2 to the first plus f double prime of 2 over 2 factorial times x minus 2 squared plus f triple prime of 2 over 3 factorial times x minus 2 cubed. Now, okay, let's see what we get. ln 2 plus 1/2 x minus 2 minus 1/8 x minus 2 squared. And then for the last term, f triple prime of 2 is 1/4. 3 factorial is 6. 4 times 6 is 24. So we get plus 1 over 24 times x minus 2 cubed. And now that I'm looking at your textbook, they stop here. So apparently the first 4, when they say find the first 4 Taylor polynomials, they mean that includes the 0th one. So this is the 1, 2, 3, 4, but anyway, since we started the index at 0. So there's P3. You could get the next one, right? The 4th order. That's the thing. This is the 3rd order, but it's the 4th on the list, I guess. So that's kind of a confusing thing. But that's that. Let's do another example. So what I want to do on the next couple examples is practice writing our answers in summation notation. So we'll use sigma notation on the next, when we write our answers on the next 2. So let's do, let's find the Mclaurin polynomial for 1 over 1 minus x. So f of x is 1 over 1 minus x. And since it's the Mclaurin polynomial, it's going to be about x equals 0. That's what it means to be a Mclaurin polynomial, right? But let's write our final answer in summation notation. Okay, so here we go. Okay, so f prime of x. Well, this is 1 minus x to the negative 1 power. So the first derivative is going to be negative 1 minus x to the negative 2, but then times negative 1 because you got to multiply by that derivative. So I think it's still going to be, it's the negative 1 will cancel with that negative there and make it a positive. 1 over 1 minus x squared. I wonder if that sort of pattern continues. Let's see. So this is 1 minus x to the negative 2. So the derivative is going to be negative 2 times 1 minus x to the negative 3 times negative 1. So it's actually going to be a positive 2 over 1 minus x cubed. So yeah, so I think the negatives are always going to end up canceling off. F triple prime of x is going to be, this is 2 times 1 minus x to the negative 3, so it's going to be 2 times negative 3, but the negative is going to cancel. So it's really 2 times 3, and I'm just going to leave it like that. I don't know why, but I feel like for the purpose of helping me establish a pattern a little bit later, this might be useful. 1 minus x to the 4th. I'm going to stop there and see if that is good enough. If I need more in order to figure out what the pattern is, then I'll get more. But we're going to do this about x equals 0. So let's look at f of 0. That's going to be 1. F prime of 0 is going to be 1. F double prime of 0 is going to be 1, or 2, sorry, 2 divided by 1, so 2. I'm going to have to let my dogs out here in a second. F triple prime of 0 is going to be 2 times 3, right? Because 1 minus 0 is 1 to the 4th power is 1. Anything divided by 1 is the same thing, so it's just 2 times 3. Okay, so I am kind of glad that I left it that way. Let me pause this real quick. All right, so I think I've got the pattern, right? Because notice that this is 0 factorial here. This is 1 factorial. This is 2 factorial. And this is 3 factorial. So I think if I continue onward, the nth derivative evaluated at 0, well, this is the 0th derivative, it's 0 factorial. The first derivative is 1 factorial. The second derivative is 2 factorial. So the nth derivative is just going to be n factorial. That's very interesting, because watch what happens now, right? So, so if I think of like the nth polynomial, right? It's going to be f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first plus f double prime of 0 over 2 factorial times x squared, and so forth, until I get to n. So it's going to be the nth derivative evaluated at 0 divided by n factorial times x to the n. Well, f of 0 was 0 factorial, right? So this is 0 factorial over 0 factorial x to the 0. F prime of 0 was 1 factorial, so this is 1 factorial over 1 factorial x to the first. F double prime was 2 factorial over 2 factorial x squared, and so forth. And so this is going to be n factorial over n factorial x to the n. Interesting. Okay, so this is just x to the 0, which I know is 1, plus x to the first, plus x squared, and so forth, up to x to the n. So what's the summation notation? Well, for this one, it's pretty easy. It goes from k equals 0 to n of x to the k. Isn't that interesting, though, right? That this thing is approximately, 1 over 1 minus x if x is near 0. Okay? Again, you could punch that into Desmos to convince yourself. And if you zoom in near 0, these things are going to be close to the same. Okay. Let me give you one more example like that, and then we'll talk about errors on this thing a little bit. So, example 6. let's find the nth Taylor polynomial for f of x equals 1 over x about x equals 1. And again, our goal on this problem is going to be to try to write this in summation notation. Okay, so try to come up with a general formula that we can write in summation notation. Okay. Oh, this is negative 1 over x squared, right? That's going to be negative x to the negative 2, so the derivative is going to be positive 2 times x to the negative 3. Okay, and then we're going to have a 2 times negative 3, so it's going to be a negative. I'm going to do the same trick as before. It worked out pretty nicely. Okay, if I need to come fill in more details, I will. Let's evaluate these things at 1 now. Okay. So that's not bad. I mean, this is, okay. So I'm going to say this is negative 1 to the 0th power times 0 factorial. This is negative 1 to the 1st power times 1 factorial. This is negative 1 to the 2nd power times 2 factorial. And this is negative 1 to the 3rd power times 3 factorial. So I have a feeling that pattern's going to continue. So the nth derivative evaluated at 1 is going to be negative 1 to the n times n factorial. Isn't that nice? Okay. Now, rather than writing out a bunch of terms like I did on this one, I wrote out a bunch of terms. I think I'm just going to skip straight to the summation notation because some nice things happen, right? So I know that the Taylor's polynomial, we'll call it P sub n. I know that the Taylor polynomial is going to be the sum from k equals 0 to n of the nth derivative evaluated at 1. Sorry, this is a function, divided by, sorry, not the nth derivative, the kth derivative, divided by k factorial times x minus 1 to the k. Okay, but I can plug some stuff in because I know that the kth derivative is just going to be negative 1 to the k times k factorial. And the k factorials will cancel. So it's just going to be negative 1 to the k times x minus 1 to the k. And there you go. There it is in summation notation. I guess if you wanted to know what the first few terms looked like, when you plug in 0, you get 1. When you plug in 1, you get, oh, I should have had a minus. So it's 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and so forth, right? So that's what that thing looks like. Again, kind of interesting that this is, approximately 1 over x close to 1, if you're close to x equals 1, right? Right, because it was a Taylor series about 1. Okay. So what do I have to say? What do I have left to say in this section? Well, okay, so as I've been mentioning, right, these Taylor polynomials are approximations for these functions that we're looking at. The approximation is close, but not exactly equal. And so there's going to be some error, some remainder, that's what we'll call it, right? So the function r sub n of x, we're going to define that to be f of x, which is the actual function value, minus p sub n of x, which is the approximation for it, right? So the difference between the actual value and the approximation, we're going to call that the nth remainder for the Taylor series of f. It turns out that we can bound that. Well, we can bound that if we can find a bound for the nth derivative, and that's what this remainder estimation theorem says. So it says if the function f can be differentiated n plus 1 times on an interval containing x naught, and if m is an upper bound for the absolute value of the n plus first derivative evaluated at x on that interval, then the remainder, the absolute value of the remainder is less than or equal to m over n plus 1 factorial times the absolute value of x minus x naught to the n plus 1 for every x in the interval that we're using the Taylor series or the Taylor polynomial for. So why does this help us? Well, you know, it'll tell us, for example, how many what order Maclaurin polynomial we would need in order to get a certain amount of accuracy in an approximation. So let's use an nth Maclaurin polynomial for e to the x to approximate e to 5 decimal place accuracy. Okay, so let's do that. And I know on my notes it said example 6, but I'm really on example 7 now, right? Okay, so we want to use a Maclaurin polynomial. So use Maclaurin polynomial for f of x equals e to the x to approximate e to 5 decimal places. Okay. Well, so first of all, if we want to approximate e to 5 decimal places, then that means we want the remainder. So we want the remainder, which, by the way, is less than or equal to m over n plus 1 factorial times the absolute value of x minus x naught. Well, in this case, since this is a Mclaren polynomial, x naught is 0. Maybe I'll just write out the whole thing, right? To the n plus 1. We want this thing to be less than or equal to, if we want to estimate it to 5 decimal places, then we need to go out 1, 2, 3, 4, 5. And then the 6th decimal place can't be off by more than I guess half. How would I say that? I mean, it's like the 6th decimal place has to be less than or equal to 5, right? Okay, so this is what we need. We know that x naught is 0 in this case because we're going to use a Maclaurin polynomial to do the approximation. Okay. Also notice that x equals 1 because we're trying to approximate e, which is the same thing as e to the first power, right? So x equals 1. Okay, so we know that x is 1. We know x naught is 0. We need to figure out m. Okay, we need to figure out m. But once we have m, then we'll be able to solve for n. Okay, we'll be able to solve for n so that this inequality holds. Once we know what n is, then we'll know how many, what order Maclaurin polynomial we need in order to approximate this thing. So, okay, so let's figure out what m needs to be. M is supposed to be the upper bound for, so m is an upper bound for absolute value of the n plus first derivative evaluated at x, right? Which, in other words, in this case, x is 1, so this is that, right? So let's see what that would be. Since f of x is e to the x, f prime of x is e to the x, and so is f double prime. And so the nth derivative is going to be e to the x. And for that matter, I guess so would the n plus first. And so the n plus first derivative evaluated at 1 is going to be e to the 1, or in other words, just e. Now, the tricky thing about this problem is that we're trying to approximate e. So maybe instead of using e, we should use a larger number that's maybe a little bit easier. Maybe we can say this is less than 3, right? E is about 2.7, so it's definitely less than 3. So I'm going to take m to be 3, right? So this way, m is going to be an upper bound for this number, right? So 3 is an upper bound for the number. Okay, so let's plug in what we know then, right? We know that we need 3 over n plus 1 factorial times the absolute value of x minus x naught to the n plus 1. We need this to be less than or equal to 0.000005. Okay, and then we're going to solve this inequality for n. 1 minus 0 is 1. 1 to the n plus 1 is just 1, regardless of what n is, so this thing disappears. We just need 3 over n plus 1 factorial to be less than or equal to 0.12345. I would multiply through by n plus 1 factorial, then divide through by this thing. And so this means that n plus 1 factorial let's see. So I multiplied this to get it there, and then I divided by that. So n plus 1 is really on this side now, so it's greater than or equal to 3 divided by 0.12345, which is 600,000. Okay, so we need n plus 1 factorial to be greater than or equal to 600,000. Now, to finish solving that for n, I'm just going to guess and check a little bit. So I'm going to put in a bunch of factorials. So let's see. 8 factorial is 40,320, so that's not big enough. 9 factorial is 362,880, so that's getting closer. 10 factorial is 3,628,800. Okay, so 10 factorial. So if n plus 1 equals 10, then this inequality will be satisfied. So n plus 1 equals 10. That means n has to equal 9, right? So n equals 9 satisfies the inequality. Okay, so we know that we need a 9th order Maclaurin polynomial in order to estimate e to the first power to 5 decimal places. So let's do it. Now, we did this already, I think. We came up with the Maclaurin polynomial for e to the x. Yeah, it was the very first example we did. So here it was. Okay, so there's our Maclaurin polynomial for this thing, and we need a ninth order. So we need p sub 9 okay, so we need p sub 9 of x, which is going to be 1 plus x squared over 2 plus x cubed over, it's n factorial, right? So over 3 factorial, which would be 6, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, we're almost there. Man, the factorial grows so fast, right? And 9 factorial. So x to the 9th over 362,880. Okay. Now comes the approximation. Okay. If we're this is e to the x, right? E to the x is approximately that polynomial. So e to the first power is approximately p sub 9 of 1, which is really nice because all of these things are just going to be 1, right? So I'm not going to bother to write them all out. I'm just going to go ahead and punch this into my calculator. It's 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1 over 120 plus 1 over 720 plus 1 over 5040 plus 1 over 40,320 plus 1 over 362,880. And if I punched that all in correctly, this is what you get. So we wanted to do this to five decimal places, right? To 5 decimal places. So I'm going to say, I'm going to round this off to 5 decimal places. So to 5 decimal places, we have 2.71828. Now, if you compare that to the actual value of e to the first power, to 5 decimal places, 1, 2, 3, 4, 5, we're the same. Actually, to 6 decimal places, we did pretty good. It's to 7 decimal places, that's where we start to see a difference. Okay, but there you go. So there's our approximation to 5 decimal places. Okay, so that is all I have to say about that.